Hi, I'm Dr. Saroja, retired professor in chemistry. Today I'm going to talk about free energy in thermodynamics. There are two kinds of free energies. One is Gibbs free energy represented by capital G. If a system is isothermal, that means it is at the same temperature and closed with a lid at constant pressure, it is described by Gibbs free energy, that is capital G. G is equal to H minus Ts. H is enthalpy, T is absolute temperature, S is entropy. It is the energy available to do non-pressure volume work in a thermodynamically closed system at constant pressure. Let's see the second type of free energy, that is Helmholtz free energy, represented by capital A. It is equal to E minus Ts. E is internal energy, T is absolute temperature, S is entropy. If a system is isothermal, maintained at same temperature and closed at constant volume, it is described by Helmholtz free energy. Helmholtz free energy is at constant volume and Gibbs free energy is at constant pressure. Make a note. The Helmholtz free energy is the maximum amount of useful non-pressure volume work. What is pressure volume work? Work of expansion or work of contraction of a gas. Non-pressure volume work that can be extracted from a thermodynamically closed system at constant volume. IUPAC, International Union of Pure and Applied Chemists, officially refers to the two as Gibbs free energy and Helmholtz free energy respectively. Gibbs free energy. Gibbs free energy was developed in 1870 by Josiah Willard Gibbs. He originally termed this as available energy in a system. This quantity is the energy associated with a chemical reaction that can be used to do work. Gibbs free energy is denoted by capital G, combines enthalpy and entropy into a single value. G is equal to H minus Ts, or more completely, since H enthalpy is equal to E plus PV, G is equal to E plus PV minus Ts, where E is the internal energy, H is the enthalpy and S is entropy, as H is equal to E plus PV. The change in free energy, that is delta G, delta represents the change, is equal to delta H minus T delta S. Let's see what is spontaneity of a reaction in terms of delta G. Delta G can predict the direction of the chemical reaction under two conditions. One is constant temperature, the other is constant pressure. If delta G is positive, the reaction is non-spontaneous and an input of energy, external energy, is necessary for the reaction to occur. If delta G is negative, reaction is spontaneous, occurs without any input of external energy. Let's see what is spontaneity of a reaction. For a spontaneous process, delta S for the universe is always greater than 0. Delta S universe is what? Delta S system plus delta S surroundings. Though delta S is a useful criterion to determine whether or not a process is spontaneous, it is rather cumbersome, difficult, because it requires us to calculate not only the entropy of the system but also the entropy of the surroundings. It would be much more convenient if there is a single criterion that would do the job and focus only on the system, because delta S surroundings is difficult to calculate. Gibbs free energy, G, is used to describe the spontaneity of a process. Delta G is equal to delta H minus T delta S, and for an ideal gas, delta H is 0 at constant temperature in an isothermal process. Hence, delta G is equal to this, since this is 0, minus T delta S, and it applied to just the system itself without regard to the surroundings, as delta S surroundings is equal to delta H divided by T, and delta H is 0, divided by T is also 0. Heat exchanged with the surroundings from the system is 0, therefore delta S surroundings becomes 0. Then delta G is equal to minus T delta S. Now let's see delta G and spontaneity of a reaction. Let's see the summary of Gibbs free energy and spontaneity with reference to 4 different processes. In the first process, delta H is positive, delta S is also positive. delta G is equal to delta H minus T delta S. So this is positive. Minus of plus is minus. So for the minus to be more than the plus quantity, this T delta S must be more than delta H. Therefore, delta G depends on the temperature. Delta G may be positive or negative depending on temperature. When will this reaction become spontaneous? It becomes spontaneous only when the temperature is high, so that T delta S becomes more negative than delta H. So minus T delta S is more than delta H. Only then it becomes spontaneous. This is case 1. Let's see what is case 2. In case 2, delta H is negative and delta S is positive. In this case, what happens? Delta G is equal to delta H minus delta S. Minus of plus is minus. This is also minus. T delta S is also minus. So the whole thing together is always negative. Therefore, this particular reaction is always spontaneous. Let's see case 3. Delta H is negative. Delta S is also negative. Then delta G is equal to delta H minus T delta S. Minus of minus becomes positive. So when will this reaction become spontaneous? This should be more. Delta H should be more than T delta S. So this reaction depends on T. Delta G may be positive or negative depending on T. When will this become spontaneous? Only if the temperature is low. Then if the temperature is low, what happens? T delta S becomes minus of minus less positive and delta S becomes more negative. Therefore, delta H is greater than T delta S. Therefore, this reaction becomes spontaneous only when the temperature is low. This is case 3. Now let's see case 4. In case 4, delta H is positive, delta S is negative. Then delta G is equal to positive. Minus of minus is also positive. Positive is always positive. Therefore, this reaction is never spontaneous because delta G is always positive. So these are the 4 different combinations of delta H and delta S for us to calculate delta G and predict the spontaneity of a reaction. Now let's see how to calculate delta G. Let's take an example. Calculate delta G at 300 K for the reaction 2 nitric oxide gas plus oxygen gas giving 2 nitrogen dioxide gas. Delta H is minus 120 kilojoules. Delta S is minus 150 joules per Kelvin. Delta G is equal to delta H minus T delta S. Now here one unit is kilojoules, the other unit is joules. Therefore, we have to convert delta S also into kilojoules. Convert delta S from joules to kilojoules. How do we do this? Minus 150 joules per Kelvin into 1 kilojoule is equal to 1000 joules. So 1 kilojoule divided by 1000 joules. So this becomes minus 0.15 kilojoules per Kelvin. Substitute this in the equation. Delta G is equal to delta H minus T delta S. Delta G is equal to delta H is minus 120 kilojoules minus 300 Kelvin is absolute temperature into minus 0.15 kilojoules per Kelvin. So that becomes minus 120 kilojoules plus 45 kilojoules. All this is equal to minus 75 kilojoules. Since there is a negative sign for delta G, it is a spontaneous reaction and delta G value is minus 75 kilojoules. So like this we can calculate the value of delta G and also predict the spontaneity of a reaction. Now let's predict the spontaneity of another reaction. In the Haber's process of manufacture of ammonia, nitrogen gas reacts with 3 hydrogen gas giving 2 ammonia gas. Delta H is minus 93, this is kilojoules per mole. Delta S is minus 198 joules per mole. Make a note, the units are again different. At what temperature will the above reaction become spontaneous? The fact that both the terms are negative means that the Gibbs free energy equation is balanced and the temperature, it is temperature dependent. Delta G is equal to delta H minus T delta S. We do not know T. Delta G is equal to minus 93,000. Why? 93 kilojoules is equal to 93,000 joules minus T we do not know into minus 198 is delta S. So if delta G is equal to 0, these two must be equal to each other. If delta G is 0, the system is at the limit of spontaneity. Then minus 93,000 joules is equal to minus T into minus 198. So T is equal to minus 93,000 divided by minus 198. That is 469 Kelvin. Now let's see when will this delta G become negative. Minus 93,000 joules minus 469 into minus 198, minus of minus will be plus. So this plus value must be less than this minus value. When will this be less? When T is lesser than 469, this positive value will be lesser than the negative value. T delta S will be lesser than delta H. Only then delta G will be negative. That means below 469 Kelvin only, below this temperature only, this reaction is spontaneous, as minus delta H is greater than T delta S and delta G is negative. So like this we can calculate the temperature at which the reaction becomes spontaneous and delta G becomes negative. So this way we can predict the spontaneity of a reaction. Thank you. Thank you very much for a patient hearing, and if you like my video, please do subscribe. And next time I'll come up with another interesting topic from chemistry. Thank you so much.